All right. So last class I was trying to explain these cluttered slides. I was talking about a 2C 2D velocity field. 2C 2D velocity field. I took a small fluid element and I was trying to track the various vertices of that fluid element. The vertices of a fluid element are what? They are fluid particles. And how do we track them? We track them by looking at their velocities at time t and multiply that by delta t. That takes us to the new location. So this is the way I was tracking these fluid particles or the vertices of fluid element. So this slide again, it's a reminder what kind of information we required for this tracking. Things in red here are the coordinates of vertices A, B, C, D at what time? These are the coordinates of those vertices at what time? At time t. All right. And what I have shown here in green color are the velocity components, local velocity components at the four vertices again at time t. So this I am treating as my base location. There I am saying the velocity components are v1 and v2. Using those values and their derivatives, I can write the velocity components at t, at time t in this manner. Okay. So this is truncated Taylor series up to first order. Okay. During the online lecture, I was trying to highlight why these indices are what they are. So this is v1. I am trying to look at the first component of velocity. That's why I have v1, one here and one here. But then I have here delta x1, del x1, delta x1, because b is displaced from a in even direction by this much distance. By same token, we have here derivative of v2 with respect to still x1 and delta x1. If you go to this vertex D here, this is v1, this is v1, not this, D is here. This is v1, v1 because it is about the first component of velocity, but here the derivative is with respect to x2 because this point is displaced relative to a in two directions. So that's why you get 2 here. Okay. So I hope you are able to follow this, but the best way to ensure that you have followed and digested it well is to derive it on your own at least once. Why is V3 not coming here? Why is V3 not coming here? Because I am considering right now a 2C 2D velocity field. Okay, since it's 2C, V3 is 0, 2 componential. All right. Here also I have not written the third coordinate. The third coordinate is actually x3 for all of them. For all of them, it is just x3. And there will be no change in x3. This plane ABCD, this face ABCD will continue to be in the same plane at time t plus delta t for a 2C 2D velocity field. Okay. And then using the velocity, local velocity and delta t, we wrote these coordinates of all the four vertices of the fluid element at time t plus delta t. Okay. Then in the last class, I was trying to get an estimate of this angle, delta alpha. So AB at time t was along E1, but at time t plus delta t, it tends to misalign by this angle delta alpha. Similarly, AD, which was originally along E2 direction at time t, tends to misalign, and it develops this angle delta beta, which is shown here. I was trying to get an estimate of those angles, and it turned out that this is fractional change. Delta alpha, delta beta, I did estimate, but I have not included them here. This is about length of AB. How the length of AB changes with time. And specifically, I am interested in this fractional change in the length of AB. The length of AB at time t plus delta t minus length of AB at time t divided by length of AB at time t, and in the limit delta t going to 0. This is what I was interested in. So delta alpha, delta beta I derived, but I am not reviewing it right now. You can go back to the lecture 10 notes and see the expression that we got. Okay. So to get the length, these lengths, I dropped a perpendicular from B to the direction of E1, and I call this point of intersection as M. And then I approximate AM, this length, to be almost equal to the length AB. Strictly speaking, it is AB times cosine delta alpha, but delta alpha is small in the limit of delta t going to 0, and that's why I approximate this as AB itself. So I want to say that length of AB at time t plus delta t is approximately the same as the length of AM at time t plus delta t. And then I'm saying that the length of AM at t plus delta t is one coordinate of B at t plus delta t, okay, minus one coordinate of A at t plus delta t. I go back here. At t plus delta t, I have the 1 and 2 coordinates of all the vertices listed here already. I am going to pick up one coordinate of B from here and one coordinate of A and put in this expression here, and that helps me find length of AB at t plus delta t as this. Yeah. Length of AB at t plus delta t as this entire thing actually. This is the one coordinate of B, and this is the one coordinate of A. So this turns out to be the length of AB at t plus delta t. So since I want to find the rate of fractional change in length of AB, I'm going to get length of AB at t plus delta t from this. Length of AB at t is delta x1 itself, divided by delta x1, which is the length of AB at time t, divided by delta t. When you simplify this in the limit delta t going to 0, you get a very simple expression. Rate of fractional change of length of edge AB as del v1 del x1, where all derivatives are at time t and at the location where vertex A was at time t. that is x1, x2, and x3. I stopped here in the last class. Next, I want to find the rate of fractional change in length of edge AD, this length. Okay. To estimate that, I am going to drop a perpendicular from D on this line. I call that point of intersection as N. Again, I invoke a similar approximation which I used earlier. AN is strictly speaking AD times cos delta beta, right? And then delta beta being small, I will say AN is approximately equal to AD at time t plus delta t. Okay, length of AD at time t plus delta t is approximately length of AN at time t plus delta t. So rate of fractional change of length edge, rate of fractional change in length of AD, this is the way we have defined. Length of AD at time t plus delta t minus length of AD at time t, length of AD at time t 1 by delta t, limiting value delta t going to 0. Length of AD at time t plus delta t, I argued on my previous slide, is almost same as length of AN at time t plus delta t, and then length of AN at time t plus delta t, I am saying that is 2 coordinate or the second coordinate of D at t plus delta t and minus the second coordinate of A at t plus delta t. Earlier it was 1 coordinate of B minus 1 coordinate of A. Here it is 2 coordinate of D minus 2 coordinate of A. I go back to the previous slide. I get this 2 coordinate of D at t plus delta t, and this is the 2 coordinate of A at t plus delta t. That turns out to be what I have here. Lot of algebra. I don't know what's the better way to explain it. It may sound a little boring as I am saying many times length of this, length of that. The best way is to derive it once on your own, and then you will feel confident about the understanding. So eventually I'm going to put everything here in this expression and set the limit delta t going to be 0. It turns out that the rate of fractional change in length AD turns out to be a simple expression del V2 del X2. Okay, so there is a pattern emerging. The rate of fractional change in length AB was del V1 del X1. AB was del V1 del X1. AD is turning out to be del V2 del X2. So AB is the length which was originally along one direction, and that's why you got del V1 del X1. AD is the edge which was originally along E2, second unit vector. So that's why you get 2 and 2 here. The SI unit is per second. So meters per second divided by meters turns out to be per second. All right. Next, we want to find the rate of fractional change in the volume of the fluid element. Fractional change in the volume, which we define in this manner. Vol means volume. Volume of the fluid element at time t plus delta t minus volume of the fluid element at time t divided by the original volume at time t, then 1 delta t here, because it is a rate at which things are changing. You set delta t to this limit. That's what we are interested in finding. Now, how am I going to get an expression for this? When I say getting an expression, what I mean to say, this is a physically sensible quantity. I want to express that in terms of what? In terms of velocity field or its derivatives. That's my quest. That's what I have been trying to do. I defined a bunch of physically appealing quantities, like rate at which two edges are collapsing, rate at which this edge is changing its length, rate at which the volume of the fluid element is changing. These are all physically sensible quantities, and my quest has been to express those quantities in terms of the background Eulerian velocity field. Okay. Same thing I want to do here. I present some arguments. Since delta t is small and consequently delta alpha and delta beta are also small, so I'm going to approximate the volume of fluid element at t plus delta t as simply as the product of length of AB, length of AD times delta x3, which is the dimension of the fluid element in the third direction at t plus delta t. Now this is the exact expression if at t plus delta t also the fluid element is exactly a cuboid, then this formula is exact, right? A cuboid of dimension ABC will have the volume ABC product, right? But at t plus delta t, the cuboid has now become distorted, true. But what we are saying is that the level of distortion is very small. That delta alpha, delta beta are all very small, and thus we will work with this approximation. That still the volume is simply the product of the lengths of the edges, but at time t plus delta t. The first order approximation. Make sense? Okay. So length of AB, what is going to happen on the next slide is length of AB at time t plus delta t is required. I am going to make one more approximation. I am going to approximate length of AB as length of AN, what I did on the previous slide. AM. Length of AB I will approximate as length of AM. Length of AD required in the volume I will approximate as AN. Okay. That's what I am writing here. AM, length of AN multiplied by delta x3. Length of AM, how you will get? Same way I got it when I was talking about the rate of fractional change in length AB, which is what? One coordinate of B minus one coordinate of A, that comes here. Length of AN, two coordinate of B minus two coordinate of A at time t plus delta t. You will get these expressions. Okay. And then delta x3. You expand it fully. You take this whole product. There are so many terms in this. Even up to first approximation, there are so many terms. One by one, I have taken the product of all factors. And then I am going to put all this here. That is the volume of fluid element at t plus delta t. This whole bunch is the volume at t plus delta t. What is the volume of the fluid element at t? At t. Simply delta x1, delta x2, delta x3. That's what I chose, the dimensions of the fluid element. So you insert this here. Few terms will cancel out. And then you will impose the limit delta t going to 0. You will again arrive at a very, very simple expression which is written there. So rate of fractional change in volume of fluid element is turning out to be the sum of rate of fractional change in length AB plus rate of fractional change in AD. All right, that is it's quite simple, despite the fact that you had so many terms here. In the limit delta t going to 0, that's what it turns out to be. Okay. I'm summarizing what I have done today and in the last online class. For a 2C 2D velocity field, we are trying to, when we try to characterize the deformation rate of a fluid element, We defined the fractional rate of extension of edge AB as this. We defined, based on physical understanding, we defined it to be like this, and then we derived using the background Eulerian velocity field this expression. Okay? You understand the difference here? Defined and derived. We defined this based on our physical understanding, and then we derived using the background velocity field and truncated Taylor series that this physical quantity must be related to the background velocity field in this manner. Fractional rate of change in length AD defined in this manner turned out to be this. Derived. Rate of fractional change in volume, I derived it just on the previous slide, defined in this manner, derived to be this. Okay. And these are about angles, which I completed in the previous class. I want to remind you again. Rate at which edges AB and AD, which are oriented along the unit vectors E1 and E2 at time t, tend to align towards each other. Physically motivated quantity defined. दो edge जो perpendicular थे वो अब at what rate they are departing from being perpendicular, we defined that to be this. Turned out to be dependent on the Eulerian velocity field in this manner. Full derivation in the previous lecture. So here you see when you talk about the two angles or the two edges collapsing or falling on top of each other, when you talk about that, see the change in indices that have happened. Right? जब एज लेंथ की बात करते हैं तो 1 1 आता है या 2 2 आता है, बट दो एजेस की बात करते हैं तो क्रॉस हो गया, del v2 del x1 del v1 del x2. And then I defined another quantity, the average angular velocity vector of this fluid element. I defined it to be like this. Delta alpha minus delta beta by 2 delta t. It turned out to be this. Again, there are cross terms, but there is a minus term. Remember the difference of between averaged angular velocity and the angular velocity of a rigid body? मैंने बताया था last class में. Anybody remember? Why am I adding an extra adjective here? Averaged angular velocity. APL 100, it was just angular velocity. If you have a rigid body, it has a unique angular velocity vector. You take any line segment on this rigid body and try to see the rate at which its orientation is changing with respect to the coordinate system which is fixed to the frame. This is how angular velocity was defined. Rate at which a line segment is changing its direction or orientation. That was angular velocity of a rigid body. Interestingly, for a rigid body, you take this line segment, or any line segment, every time the rate of change of orientation will turn out to be the same. In other words, I'm saying a rigid body has a unique angular velocity vector, right? It's not associated with a particular line segment or a point. Here I'm talking about averaged angular velocity. So clearly, this is different from angular velocity. What is the significance of this word average? I explained it in my online class. I said that since a fluid element is not a rigid body, so what happens is that the rate at which this edge is misaligning will be different from the rate at which this is misaligning. If it was a rigid body, what will happen is that if this is a rigid body, if this angle is delta alpha, delta beta is got to be minus delta alpha. You think about it. It has to happen. This is along E1, this is along E2. ये एज जितना इधर जाएगा इस एक्सिस से, ये वाला एज उतने ही एंगल से उसे वर्टिकल एक्सिस से शिफ्ट होगा. Rigid body, right? That will happen all the time. But for a fluid element is not a rigid body. So these two have their own minds. They have their own minds. Delta alpha कुछ हो गया, delta beta कुछ और हो जाएगा. So I cannot define angular velocity, but we insist that we want to define a quantity that gives me some measure, some averaged measure of how the fluid element is rotating. We define a new quantity which is the averaged angular velocity, which is what? Delta alpha टू क्यों आया? टू क्यों आ रहा है? एवरेज लिया, दो लाइन सेगमेंट का अलग अलग मेजर किया क्या एंगल है उनका, और सिंस दो लिया है तो उनका ऐड करके दो से डिवाइड कर दिया. I ask what is the average age of the student, average student age in this class. I take your age, take your age, दोनों को ऐड किया, दो से डिवाइड. अगर पांच को किया तो पांच से डिवाइड. That's why you are getting this. Okay, so keep in mind this is average. And माइनस इसलिए आ रहा है क्योंकि we want this definition. We want this definition to go and coincide with the angular, the unique angular velocity vector of a rigid body in case this starts behaving like a rigid body. आप ये definition लो, ये नहीं, ये definition लो, and you impose this condition. क्या होगा? Delta alpha plus delta alpha by 2 divided by delta t. और rigid body का definition क्या है? वही है, delta alpha by delta t. So to make it coincide with the unique angular velocity definition of a rigid body, I put minus. Is it clear? All right. Okay, so this is what we have done so far. Now what I'm going to do is to extend whatever we have derived, sort of extrapolate those expressions for the general 3C 3D case. That's what I said in the previous class also. I actually wanted to derive these things for a general 3C 3D velocity field, but I was reluctant to do it in that way. Why was I reluctant? I told the reason also. Lot of algebra. आप अभी देखो 2C 2D में पूरा slides cluttered हो गया. So this is the way I do. This is the way it's done in other books also. पहले 2C 2D का derive कर लेते हैं. We get an idea how it has been done, and then we say that कि अगर 3C 3D में हम करें ऐसा, तो result जो मैं present कर रहा हूँ वही आएगा. All right. If you are curious, you derive it yourself. Okay, but that will not be part of the any exam. I will not ask you 3C 3D derivation. Just too much algebra. So I'm going to use whatever results I had for 2C 2D and extend it to 3C 3D. Let's see how things turn out to be. This is the fluid element, cuboidal fluid element. First question, rate of fractional change in the length of AB. That is defined in this way. Even in 3C 3D case, it will turn out to be the same what was in 2C 2D. As far as length AB is concerned, same situation. Del V1, del X1. All right. Second, rate of fractional change in length AD is, of course, this is the definition. This is the derived expression. Same as 2C 2D. Same thing goes for rate of fractional change in length AE. It will turn out to be del V3, del X3. Of course, in 2C 2D case, वो zero था. But I am using these results and extrapolating, and I'm saying that this is what it will turn out to be. Again, subject to verification, but trust me, this is what it will turn out to be. There is a clear pattern. I hope you recognize that pattern, and that will keep you aware what edge we are talking about and what components of velocity derivative should come. Rate of fractional change in volume of this fluid element defined in this way, it will turn out to be this. What's happening? Rate of fractional changes in all three lengths, AB, AD, and AE, will all be added together, and that's what you will get as rate of fractional change. SI units of every quantity here is per second. Right? It is rate, that's why per second, और सब कुछ fraction में है, that's why length मीटर या मीटर क्यूब नहीं आ रहा है, क्योंकि हमेशा हमने normalize कर दिया है original value से of the respective quantity. All right. Now let's come to the projections, this complicated figure that I showed in the last class. Rate at which the projections of ABAD, this is A, and remember A is very special vertex. A is very special vertex because A has the position vector as X, or Cartesian coordinate system, it is A which is at x1, x2, x3 at time t. This is at time t. Of course, ये distorted है तो ये t plus delta t है, but A was at, तो यहाँ तो लिखा है, so at time, this is at time t, x1, x2, x3. A is the base location. Okay, so rate at which AB and AD projections on which plane? x1, e1, x2, e2 plane. So you consider a plane which is this, containing point A and this E1 and E2. On that plane, B is somewhere here actually, but I'm taking the projection of B here. D is somewhere here, I'm taking the projection of D here. So that this is B prime, this is D prime, and then I called this angle as delta alpha 3 and this angle as delta beta 3. So rate at which projections of AB and AD are collapsing towards each other on this plane is defined in this way, will turn out to be this. Okay. Rate at which the projections of AD and AE on which plane? On E2, E3 plane, is plane पे. Projections of which points? AD and AE. So D का projection यहाँ है, E का projection यहाँ है. I am using double prime. Angles, relevant angles are delta alpha 1 and delta beta 1, the way they have been drawn. Delta alpha 1 is like this, delta beta 1 is like this. So this physically appealing sentence is mathematically this, and it, when you derive it, it will turn out to be this. Look at the indices. 2 and 3 plane, projections on 2 and 3 plane, and that's why here 2 and 3 are appearing. Projections on x1, x2 related plane, that's why 2 and 1. Patterns. Okay. And finally, the rate at which the projections of AE and AB on which plane? This plane. 3 and 1 plane. Tend to align with each other. Projections of E and B. AE and AB. So vertices जो है वो E थे, E और B. Triple prime projections. Angles are delta alpha 2, delta beta 2. This is what it means. This English sentence means this. Turns out to be this. 1 and 3. 1 and 3 क्योंकि 3 और 1 यहाँ पे. Okay. I'm going to remove all this because I'm going to upload it I hope at least this much familiarity you are able to gain during the class itself. 1, 3, 1, 2, at least that much. If you register, I think it's enough for the time being. All right. The component of the average angular velocity. So when I talked about 2C, 2D, there was one component of average angular velocity which was relevant, and that I was denoting by this omega 3. In 2C, 2D case, only one scalar component of the so-called average angular velocity vector appears, and that was omega 3. But for a 3C, 3D velocity field, other two components of the vector, omega 1 and omega 2, will also be non-zero in general, and they will be, as I have, the expressions are here. The component of the average angular velocity vector along the unit vector E3 is defined in this way and derived in like this, same as 2C, 2D. So there is nothing new here, but the other two components are new. The component of the average angular velocity vector along the unit vector E1, along this unit vector, that is defined in this manner. You see delta alpha 1 minus delta beta 1 by 2 delta t. So I'm talking about these angles. So when you talk about average angular velocity vector component along this direction, you have to go to the plane which is perpendicular to this direction, and then look at the angles which are delta alpha 1 and delta beta 1. Whereas here, you were looking at the component of the vector in the third direction, and you were interested in the angles that were in a plane perpendicular to the three direction. And that's why here delta alpha 3 and delta beta 3 came. Here it is delta alpha 1, delta beta 1. Looking at this pattern, I am writing it, but again, if you can verify, it will turn out to be true. So what pattern you see here? This is 3. It turned out to be 2, 1, 1, 2. I am following a cyclic order here. So 3 becomes 1 here, 3 becomes 1, and then I have changed these indices also in the same cyclic order. So 3 became 1, so 2 according to this becomes 3 here, 1 becomes 2 here, 1 here it was 1, it becomes 2, and here it was 2, becomes 3. So in that manner, if you rotate the indices, you will get the right expression. And finally, omega 2, which is the average angular velocity vector along unit vector E2, I consider this component of the angular velocity vector. I focus on these angles, which are on a plane perpendicular to that. This is the definition, and this is the expression which you can generate again using 1, 2, 3 cyclic order. Is it following the order? Third वाला देखना, omega 2. 4.36 से 4.37 follow हो रहा है, following that order. Indices are fine. Yeah. Now, having derived all these expressions, derived some of them and then extrapolated for other cases, and then accepting that all those expressions are sensible, I want to discuss the conditions under which I can, the prevailing conditions under which I can conclude whether a fluid element, which by its nature is non-rigid, but under certain conditions it can behave like a rigid body. You understand this proposition? In general, it is a non-rigid body, but are there certain conditions under which at least instantaneously it is behaving like a rigid body, right? Let's have a look at that. Now, this is the diagram I have been showing you earlier for a 3C 3D velocity field. I had a cuboid and then I showed a distorted shape. My idea is to just draw a kind of a freehand sketch and highlight the fact that it will get distorted. That's why I drew it like that. However, it turns out that with all the coordinates of all vertices available at t plus delta t, इन सारे vertices के coordinates at t plus delta t available हैं, you can verify that at time t plus delta t, this fluid element which was cuboid at the beginning will become a parallelogram, will become like that. Follow what I'm saying? Cuboid will become a parallelogram, can be derived with the coordinates. Parallelogram मतलब क्या है? ये 4 edges जो मैं draw कर रहा हूँ यहाँ पे, these 4 edges will be the same, and then if I look at another group of 4 edges, they will be the same, and then they will turn out to be the same in the limit of delta t going to, in the limit of delta t being small. So you think about it, since it is a parallelogram and I have derived expressions for the rate of fractional changes in 3 lengths, right? That's what I did. For 3 edges, I derived the fractional changes. But since it's a parallelogram, I have actually described, or I have the expression for the rate of change of every edge, right? All right. Similarly, this angle, I measured the angle or the rate at which AB and AD were collapsing, and then the rate at which AD and AE were collapsing, and the rate at which AE and AB were collapsing. But since it is a parallelogram, I have also described, or I have the expressions, the rates at which other edges are also collapsing. Will you agree with me? Because it's a parallelogram, right? So in that way, whatever expressions I derived so far, that gives me complete description of all edges and all angles of this small fluid element. Follow what I'm saying? All right. So I have all the information, and that's why I am in a position to identify the conditions under which this cuboid refuses to become a parallelogram. Actually, a cuboid is also a parallelogram, strictly speaking, but when I say parallelogram, I mean to say the angles are no more 90 degrees. Okay. These are the conditions. Conditions required for a fluid element to behave like a rigid body at time t. Conditions. All derivations at the location of fluid part. All derivatives are at the location of the fluid particle at time t. Just reminding you. Condition 1. This should hold good. Why I'm saying this? If this holds good, then these 3 edges, or rather these 4 edges, are not changing their lengths. Right? If they are changing their lengths, it's not rigid. So first necessary condition, I'm not saying sufficient. The first necessary condition for this to behave like a rigid body is that we should control these 4 edges. Control these 4 edges means this should be 0. Condition 2, this should hold good. Because if this holds good, then this edge, this edge, this edge, and this edge will not change its length. Third condition, the remaining edges are controlled. This, 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 and this. So if these conditions are fulfilled, then at least we can say that the edge lengths are not changing. And it actually follows that if all these 3 things are fulfilled, then we know that the sum will also be fulfilled. This condition for sum. which means that the volume is also not changing. So these conditions imply that automatically. However, keep in mind that there could be conditions in which this is 0, but you cannot conclude all of these are 0. Implication doesn't follow that direction. But individually these are 0, then this is also satisfied. Is it good enough? Is this set good enough to conclude that it is behaving like a rigid body? No, because the edge lengths may not change, but this can happen. Angles may change, right? And that is why there are more conditions required for it to behave like rigid body. Condition number 4, this should be 0. I have not written the full sentence. I have written a common sentence here. Individually, if these are 0, then what it means is all angles which were perpendicular, which were pi by 2 at time t, all edge angles, not changing with time at delta t. These 3 should be followed. So in total, there are 6 conditions to be simultaneously satisfied for a fluid element to instantaneously behave like a rigid body. Does it make sense? It's quite a tall condition. We don't know many flow fields in which all these conditions will be simultaneously satisfied. There are a couple of them. We will look at them later on. But most of the times in real life, very hard to fulfill these conditions. But the reason I am highlighting this, because this gives us an idea when a fluid element departs from its rigid behavior or when it behaves in a non-rigid manner, how it is quantified or how it is different from its otherwise rigid behavior. The indicators are all here, 6 conditions we derived. Any one of them is non-zero, non-rigid. Now, if a fluid element is behaving like a rigid body at a given time, all 6 conditions are satisfied, guess what? The average angular velocity vector will become the unique angular velocity vector of the fluid element. Going back to what you asked. जितने angles थे, सब equal or opposite direction हो जाएंगे. So average angular velocity vector will collapse or become the same as the angular velocity vector of the fluid. That's what I have written here. This is the average angular velocity vector. And this, when I write in this manner from APL 100, the angular velocity, vector of a rigid element. Okay. Take 2 more minutes and then let you go. Now all these expressions that we derived for those physically appealing quantities, various rates of changes, you would have observed by now that all of them involved derivatives of velocity. Del v1, del x1, del v3, del x1, so on. Everywhere there are derivatives. Now those derivatives that we have seen so far, we can show that they all are various components, scalar components of a tensor of second order. All those derivatives of velocity are scalar components of a tensor of second order. What is that tensor? So V is the Eulerian velocity field. If I take this, if I hit the velocity vector by this operator, del operator or the nabla operator, what do I get? I get gradient of velocity. You remember? First, second, third classes I was talking about Any tensor you can take the gradient, and then the resulting tensor is a tensor of order 1 more than the original tensor, right? So velocity is also a tensor. It's a vector. I can hit it with this del operator. It becomes so-called the velocity gradient tensor. Now, if I choose my working coordinate system to be a frame fixed Cartesian coordinate system, this is how I will write it. Em del del xm Vp. I can put it like this. In the full expanded form, it will be what I have here. Please see if the indices are okay or not. 9 components, even E2, and so on. 1, 3. Look fine? Okay. Now, so this is the full version. Now let's make another tensor. Let's define another tensor, which is this. What is this T here? Transpose. The original second order tensor, the transpose of that itself added and divided by 2. Let's use this new symbol S for that. This tensor, which we just defined, is called the strain rate tensor. Strain rate tensor. In solid mechanics, they might have defined the strain tensor by now. We are interested in what is called the strain rate tensor. It is a symmetric tensor, guaranteed. Why? Because it has been generated in this manner. Okay. Now, mind you, this tensor S, just like the velocity field, is another Eulerian field. Right? V is Eulerian field. I take gradient of that, that also becomes an Eulerian field. I take transpose, that also is Eulerian. I add them, both of them. Resulting thing is also an Eulerian variable. Okay, stop here. सेव कर लेंगे. हाँ PDF.